Hello, everyone. This is Yonggan from Rice University. Today, I will present our work, drawing robust squash tickets. Subnetworks with Inborn robustness are found within randomly initialized networks. Although deep neural networks have achieved record-breaking performances on a lot of tasks, they are known to be vulnerable to adversarial attacks. That is, an imperceptible perturbation in the input can mislead the prediction of the models. And previous work show that over-parameterization is deemed to be necessary for model robustness against adversarial attacks. This indicates a dilemma between DNN's robustness and efficiency, making it challenging for deploying robust while complex DNNs on resource-constrained platforms. Therefore, to bring both efficiency and robustness, we aim to build robust, sparse networks. One inspiring work for us is the lottery ticket hypothesis, which finds that subnetworks within dense networks can be trained alone to achieve comparable accuracies to the dense ones. And identifying such lottery tickets requires to start from a pre-trained model and do iterative training and pruning process, as shown in this figure here. On top of that, we ask an intriguing question that, can we find robust subnetworks within randomly initialized networks without any model training? The answer in our work is yes. The key finding of our work is the existence of robust squash tickets or ISTs. That is, subnetworks with inborn robustness hidden in randomly initialized networks without any model training, which can even match the robustness of the corresponding dense networks. Different from the iterative training and pruning process for identifying lottery tickets, neither the original dense network nor the identified ISTs need to be trained, which make our ISTs principally different from lottery tickets. In addition, the existence of ISTs is interesting, since we know that the random networks make random predictions, and the naturally trained models will have near zero robustness against strong attacks. However, the ISTs identified from the random networks without any model training have both different natural and robust accuracy. Here are our main contributions. We are the first one to identify the existence of ISTs from randomly initialized networks with inborn robustness without any model training. And we propose a generic adversarial search framework to search for ISTs. On top of that, we conduct extensive experiments to identify and study the existence and properties of ISTs under different conditions to provide insights for the role of initialization and over-parameterization in model robustness. Furthermore, we identify the poor adversarial transferability between ISTs and propose a random IST switch technique as a novel defense method. Here's the outline of our presentation today. We will next introduce the methods to search for the IST and then thoroughly study their existence, properties, and applications. The first question is that, how can we find robust subnetworks within randomly initialized networks? Two requirements need to be satisfied. First, we need to make the search process aware of robust training objective, and we also need to ensure the sparsity of the joined subnetworks. To this end, we just modify the SOTA adversarial training process into an adversarial search method. As shown here, we will apply a learnable mask N on top of the randomly initialized model weight data, and we will also exert a sparsity constraint on the M here. And we will update M and fix the model weight data via this minimax problem. And in particular, during the forward process, we will activate the top key value in M, and during the backward process, we will update all the elements in M via a twist-through estimator. And for more details about our search methods, please refer to our paper. Next, we will study the existence of ISTs across 4 networks and 3 datasets. And by default, we will adopt a signed K-mean constant initialization with an element-wise sparsity pattern, and the reported accuracy are based on the PG20 attack with an epsilon of 8. And we have an extensive ablation study of all these design factors in our paper. As shown in this figure, we report both the robust accuracy and the natural accuracy under a wide range of weight remaining ratio, that is 1 minus sparsity And the different colors here means different networks. And the dashed line here is the robust and initial accuracy achieved by the adversarial trained dense network correspondingly. And from this figure, we can observe that the ISTs can achieve a comparable, robust, and natural accuracy with adversarial trained dense networks under a wide range of weight remaining ratios. For example, the ISTs with a sparsity ratio of 90% identified from the wide ResNet32 can achieve a notable higher robust and natural accuracy with a reduction of 60% of parameters compared with the adversarial trained ResNet18. And this can be consistently observed on the large-scale internet. And here from the table, we just try to identify the ISTs from ResNet 50 and ResNet 101 with different weight remaining ratios and different perturbation strengths. And for example, we can find that the ISTs identified from the ResNet 101 can achieve 3.56% higher robust accuracy with a 4.31% higher natural accuracy compared with the adversarial trained dense ResNet 18 on the comparable model sizes. In addition, we find that the ISTs identified from more over-parameterized networks achieve a better, robust, and natural accuracy than those from lighter networks. And we can consistently observe the existence of ISTs across different model initialization methods, different sparsity patterns, and different adversarial search variants. Next, we will study the properties of our ISTs. We asked two intriguing questions that, what about the performance if we further fine-tune the identified ISTs? And what will be performance if we apply the adversarial search process directly on top of the pre-trained networks? And for the first question, how do the vanilla ISTs perform as compared to ISTs with fine-tuned mobile weights? We propose two settings of fine-tuned ISTs. That is, fine-tuned ISTs starting from the model weights inherited from the vanilla ISTs, and also the fine-tuned ISTs with re-initialized model weights. And in this figure, we just show the robust accuracy across different weight remaining ratios. And we also do zooming here for the relatively low weight remaining ratio, which are the commonly adopted sparsity in previous learning works. And from this figure, we can see that compared with the fine-tuned IST, the vanilla IST without any model training can already achieve a comparable robust accuracy under a wide range of weight remaining ratios. And the fine-tuned IST with inherited weights can mostly achieve the best robustness among the three IST variants on the low remaining ratio. However, the fine-tuned IST with re-initialization can only achieve a comparable or even inferior robustness compared with vanilla IST on the low remaining ratios. And the key insight here is that it reveals another longitudinal phenomenon, that is, the IST being a better initialization as fine-tuned ISTs with inherited weights are more robust than the re-initialized ones. And such insights are consistent across different models and datasets. The second question is that, can subnetworks search from trained networks be more robust than ISTs? So we just directly apply the adversarial search scheme on top of the trained method and propose two settings of robust trained tickets. That is, the natural ITT search from naturally trained networks and the adversarial ITT search from adversarially trained networks. Based on results here, we can observe that the adversarial ITT can generally achieve the best robustness. However, the natural ITT can only achieve inferior robustness and also natural accuracy compared with the vanilla ITTs without any model training. So why the natural ITTs are less robust than ISTs? We find that naturally trained models are more sensitive to the perturbation on the input. So in this figure, we show the normalized distance between the last feature map generated by the clean input and the noisy inputs under different perturbation strength here. And we can see that the normalized distance is largest in the naturally trained models compared with the randomly initialized models and the adversarially trained models, leading to the less robustness of the natural ITT identified from the naturally trained models. And next, we will discuss the potential application of our IST. And the question here is that how to practically utilize the identified IST. An encouraging observation is that the adversarial transferability between different ISTs with different weight remaining ratios are actually very poor. As shown in this figure here, we just want to generate the attack based on one IST and use that attack to attack another IST with a different weight remaining ratio. And the corresponding robust accuracy is annotated in this figure. So you can see that the gap between the non-diagonal elements and the diagonal elements are actually very high. For example, the robust accuracy difference between these two elements here are up to 70%. So this indicates the poor adversarial transferability between ISTs with different weight remaining ratios. And this is consistent across different networks and datasets. Therefore, based on that, we propose a simple but effective defense method called random IST switch, randomly switch between different ISTs from a candidate IST set with different weight remaining ratios during the inference process. So if there exists a gap between the attack IST and the inference IST, the robustness can be notably improved so that the average robustness can be guaranteed. Another advantages of our I2S method is that it is parameter efficient due to the weight sharing scheme, and the same randomly inferred network can be shared among different tasks to further improve the parameter efficiency. We evaluate our I2S technique against different attacks, including PGD20 attacks, oral attack, and CWINF attack across different datasets, and we can observe a notable robustness improvement over the adversarially trained dense network. For example, we can observe a 15% higher robust accuracy over the adversarially trained wide resident 32 against PGD20 attacks. And we find that our R2S technique can consistently work on the different candidate IP sets. And more original studies and discussions about R2S against adaptive attack and also R2S advantages in supporting multitask can be found in our paper. So that's all for our presentation, and for more details, please refer to our paper or join our session.